This is a module I like to do in the morning when you're fresh. And that's one reason I do the pasta and the beads right after lunch, so that you're moving a little bit. But I'll try and go through this a little quicker, see when my target is. What is this? 45. All right, we'll have to hurry. We'll make it. Maybe on the next one. Okay. Statistical activities. Basically, same kind of formula for any process. You're collecting, organizing, and interpreting numerical facts and results so that you can make decisions. We classify and manipulate data, and manipulate is maybe a bad word, but analyze, certainly, data appropriately so that we can draw inferences. And we'll talk about inferences too. And then we assemble them for presentation, as you'll see in this presentation and the next one. Showing data in the histograms as you made is a good way than saying, all right, sigma, I equals 1 to n. Oh, God, we don't want to see that. Okay. A histogram tells a story. Okay. Other types of graph tell a really good story. So graphing data and doing good data display, we could talk about that for a whole day, but it's very important. But in the end, we're going to take those data that you collect, and we're going to make inferences, and we're going to make decisions. And those decisions have a cost impact. Sometimes good, sometimes not. Okay, and as I said, visual presentation is very good. That's kind of one of my specialties, is creating visual diagrams for, say, even multi-contaminate problems in time or space. So you get sort of the four-dimensional component. They work like a champ, especially in litigations where juries who don't understand anything say, oh, I see the pie chart, I see the pretty colors, I get it. Okay, show them a formula. Stephen Hawking said, every time you put a formula in your book, it halves the number of readers. Okay? Which is why I don't sell a lot of my books. I'm like down in the 10 to the minus 30 or something, and that sort of thing. So anyway, ultimately we're trying to reduce the decision risks. Now there's several aspects that we usually go through. We design a sampling program. I think you're getting the feel with the incremental sampling that you just don't say, go get me some samples or soil, okay? You should be designing that sampling program. Everything from the material you collect to the subsample to the lab protocols and so on. In addition, we, through the DQO process, put in an allowable level of uncertainty. We know we're always going to have uncertainty. It's just the way life is. We just try and manage it. We collect and analyze the data, and then sometimes telling others what we found is the biggest part of it. Telling the story. Not lying, but just saying, this is what it means. If you have a report that said, the concentration went up 10 times the former result, people tend to flip out. Okay, well, if it goes from 0.1 to 1, and your action level is 100, so what? But somebody can pull out that statistic and make your life miserable. So you got to manage that, okay? It's not lying, but, it's sensationalism. That's what you want to read. That's what people read in the newspaper. They like entertainment. So we're not entertainers. In fact, there's no statistical humor. That's what I always tell people. In fact, it's so bad that one thing you might learn today is that if you're at a cocktail party and you have somebody who you're talking to who's really boring, just tell them you want to talk about the latest advances in statistics, and they'll probably realize they need to fill their drink and just want, no matter how full their glass is. So I've used that a couple times. I never do it on the airplane because I don't want to torture people. All right, we're looking for how many samples, are necessary. As I said in the beginning, everybody wants to know how many. We want to minimize sample errors and bias. We want to condense, describe, and evaluate the data, present them, look at the errors, separate different populations. This can be a big deal, okay? And we don't have time to really go into that. But sometimes you have multiple populations, probably not in piles, but it is possible. And these are really challenging. Sometimes they're really fun. And hopefully you won't run into this too much, but you have to watch out for that. And then sometimes you can use correlations to assist. Probably not in pile sampling, but it can be a very useful tool. Okay, a little bit of housekeeping here. Populations, which means the whole shebang, something like this, the whole pile, has a parameter, has a mean. There is only one mean. It has only one value, okay? We don't know that mean. So by proxy of sample, we describe it through a statistic. A mean is a statistic. A variance, standard deviation, those are statistics, okay? It has a real mean and variance, okay? And we'll talk about that aspect too. But we don't know those. That's why we have uncertainty. Visualizing data, again, we hope to have a normal distribution. This one's not too bad, but you can see it's not perfect. We've got some kind of contaminant, SGS down there. We can fit a model. People can understand that. They can see it's not log normal for better or worse. If the action level is 20, well, then we got a problem. If it's 50, then we're in good shape. Just as an example, usually I have the beads, but this is a result. We'll see a couple more from a few hundred samples from the bead models. This is about as close to normal as you will ever see. Okay, as I said, I designed them to be perfectly normal, but over the last 20 years, every course I see 1 or 2 beads on the floor. Okay, chances are those are the mean values. And so, things can change. But anyway, it's looking pretty good. If you get something like that, consider yourself very lucky. Okay? We like to apply distributional models. As I mentioned, we like normal distributions. Student T's will work for smaller data sets, say 30 or less. And then log normal distributions are very common. Sometimes it's even what I call on beyond log normal, 3-parameter or worse. Those little spiky things you guys got today, yeah, that's really tough to deal with. You may have to go to another type of statistic rather than the mean. And then the Poisson distribution, that's what we were doing with the particles. Oops. Okay. So again, housekeeping, the student's T is very similar to the normal distribution. It's just a little bit wider and not quite as tall, and we use it when we have basically 30 samples or less. Here's a picture, okay? You see the normal here in the dotted line. It's got slightly higher peak than the student T distribution, but the student T has slightly larger tail. Basically, almost all of the data, 99.some% of a normal, fall within plus or minus 3 standard deviations. It's 4 for the student T. And what this does is it widens the confidence interval, saying that, yeah, we recognize that since we had a small number of samples or a small number of increments, there's more uncertainty going on. And so we add a little bit of a, I don't know if I call it a fudge factor or extra caution into our calculation. Okay. Log normal distributions, very difficult to work with. They're tricky, they're unsatisfying. It's actually very unusual to transform data. You just take the logarithm, and it should, if they're really log normal, you will get a log normal, or you will get a normal distribution as a result. A lot of times you still don't get a normal distribution. And then working in log space is very tricky and unsatisfying. So usually it's not pleasing to anybody. That's why I keep promoting the incremental sampling, because it tends to take out this log normal effect.
That's commonly found in environmental data. Is that sampling error? The reason it's coming?
I would call it sampling design more than error, but it could be sampling error. Well, it's almost semantics. Yeah, because at this point in my career, I would say using the small teaspoon, that's a sampling error. You shouldn't have done that. Okay, unless you were creating a tablespoon increment. Okay, so we could be talking semantics, but it's in that genre.
I've just heard that a lot, and I wonder why it's common in environmental. And maybe it's just because I'm environmental, I hear that. But
Well,
You'd think if it's common environmental, it'd be common in all kinds of stuff.
typically the lower the concentration you're trying to observe in a parameter, whether it's gold or lead or PCBs, the more likely you're going to have a log normal distribution. Because even if you take a big sample sometimes, you're still going to have low values. The laws of entropy work against you. Even if you have, like with TNT, a concentrated source, it tends to disperse over time. Okay, so, things want to, in some cases, dilute themselves through rain, weathering, wind, you name it. And so things could start off as really concentrated at the source and then disperse over time. On the other hand, sometimes they just occur in clumps. Okay, we can transform. Here's a typical log normal. You can get them from any number of things. These are the results of 4 throws of a die, and you get a log normal distribution. Just an example, that's kind of what they look like. Here's one that's on beyond log normal. That's what we did here with the teaspoons, essentially, although this is not data from the experiment. Here's a kind of a Monte Carlo simulation, a normal distribution. Not perfectly normal, but not bad. I'd take it. Definitely got the shape. Here's another histogram. This is the one we did just about a month ago. You can see really good correlation. Slight difference here, slight difference here, a little bit difference here, but man, somebody brought me this one, I'd have a happy day. This is a good distribution. Okay, here's another one. But those are log transform values, okay? Sometimes we're not so lucky. Sometimes it's still skewed over on that side. Okay, talk a little bit about central tendency. I've mentioned this a little bit. The mean is the average, okay? If you took a sheet of plywood or cardboard and cut it out in some funky shape, the mean would be the balancing point, okay? Where the average is, okay? Now, the median is where half of the values are above, half of the values are below. So you could have most of the values below a very low concentration. And, I'm sorry, on the histogram. But there is a middle point. In fact, you could have the median be 0 on some of our graphs that we did today. So in some cases, that statistic isn't very useful, except to tell you you probably didn't design your sampling program correctly. That's what it can tell us. And then there's the mode. That's the most frequently occurring value. As we saw today, 0 was the mode in a lot of cases. That was not a good result. If it's normal, the mode will be the mean, and that's the result we want. Because then you get symmetry, you get to use all the normal statistics that are so appropriate and comforting to people because they're familiar with them. Dispersion, what's your min and maximum value? That can give you an idea of what problem you're working with. We'll talk a little bit about that in the next module. Variance, how much variability is there? Variance is calculated as a square. You take the square root, then you get the standard deviation. And I won't bore you with how you calculate those. But I will go over the normal and just tell you kind of how that works. About 2/3 of the data in a normal distribution fall within plus or minus 1 standard deviation. Actually about 68%, so roughly 2/3. And then within 2 standard deviations, you get about 95%, and you get virtually all of the data in a normal distribution within plus or minus 3 standard deviations. Okay. So for instance, if you're just kind of doing a rule of thumb and you've got a distribution of data which may or may not be normal, but if you assume they were normal just as a swag or back of the envelope, you can say I've got data between this and this. Okay? If you divide by 6, there's 6 standard deviations in a normal distribution, you could come up with a swag standard deviation, assuming you have normal data. So just one thing to think about. It can be dangerous to use that, but you know, if it's not going to the regulator or not going to court, you know, it may give us some sense of what's happening. Here's the picture form. You can see 68%, 34 and 34. And we have the 13.5 roughly there. This is 95%. And then 3 standard deviations is 99.7%, most of the distribution. The central limit theorem is actually one of the things we use in incremental sampling. The central limit theorem says the distribution of averages from a population will be normal. So that if we take, let's say we go out to a site and take 30 samples, we get the average. And because we had some multimillionaire funding us, we did that a whole bunch of times. Took 30 samples, got another average. So if we get 30 averages, we can make a distribution of the averages, okay? Those averages will tend to be very, very normal. That's the central limit theorem. That's kind of one of the things we bank on sometimes in environmental data analysis. And here's an interesting experiment somebody did. We start off with several different types of distributions: a normal, a uniform, a bimodal, kind of an inverse normal, and then a kind of a decline curve, I would call that here. If you sample these with, let me get the numbers here. Okay. If you take 2 averages from each of these populations, this one goes to a pyramid. This one inverts itself and starts to look normal. This one is log normal, but it's a whole lot better than this. If you increase the number of averages to 5, things are starting to look pretty normal down here. Even this one's getting whipped into shape. If you increase it to 30, basically everything's a normal distribution, but those are averages. It takes a lot of money and time to get averages for 30 sets of data, okay? But that's the normal distribution. So how do you do that? Well, increments could be one way, okay? We use increments to get an average. Increments are very good to characterize what's the average concentration at a site. And so a lot of times we just get 3. We take 3 increments, maybe of 30, 50, 60 increments. And then at 3, well, I don't have a 3, but probably we're going to look, you know, even if we start off with something like this, we're going to have something look semi-normal after 3 to 5. Okay, it really helps. Confidence limits, we won't talk a lot about this, but basically when we say we've got a mean for the population, we want to say, okay, we know there's uncertainty around the mean. How do we develop a confidence interval around the mean? A confidence interval just says, well, it's, you know, we had an average of 100, but it could be between 90 and 110 with a certain level of confidence. And we'll probably use that upper number, 110, the upper confidence limit on the mean, to say, is that greater than our action level, which might be 150? Or if it's 100, well, then that's a problem. But we use the upper confidence limit to bound our decision error. Here's some examples of confidence limits. These are inferences saying we assume it's normal, we assume the distribution works, we assume we have good data, and then we take the mean and we add and subtract a certain number of standard deviations to get a certain level of confidence. So if we have a mean of 50 and a standard deviation of 10, we have 68% confidence that the mean will be, or that actually that this interval will capture the true mean between 40 and 60, 95% confidence that we'll capture it between, if it's between 30 and 70, and 95% between 20 and 80. Well, that's quite a spread, but that's how it works. But if we want a 95% confidence that our mean is not greater than 80, we can do that. We can use an upper confidence. You calculate it just slightly differently, but basically it's the same thing. And if our action level is 100 and we have a 95%, 99% confidence that it's less than 80, we're in good shape. You probably use, I'm sure many of you, UCLs, upper confidence limits. Here it is. And I always put this diagram up because sometimes people get a confidence limit, which is the entire distribution, and a confidence limit around the mean. Here we have the mean, okay? And we're trying to develop a confidence limit around the mean. Now, usually we don't care about the limit down below the mean, but we do care about the one above because we could have had biased samples that underestimated the mean. So we add this little statistical twiddly bit to increase our confidence. Now, as we said, between here and here, you've got 99.7% of the distribution, but this could be the 99.7 confidence limit on the mean. I don't know if that makes any sense. But in other words, if we want to know the maximum value that we might encounter and we have a normal distribution, here's where we're looking, on beyond 95%. That's a data value. Here and here, we're looking at the mean. What's the confidence on the average? Not individual data points, but on the whole collection. Because say in a risk assessment where you're looking at average, that's a lot of times why we want to calculate that UCL. Error and uncertainty. This isn't quite perfect, but basically you can think of it, uncertainty is what you don't know, especially before you go out and collect the data. You don't know the variability, you don't know the concentrations. Error is what you have after the fact, or when you make decisions, you say, well, we thought it was below the action level, but it was really above, okay? Sometimes you don't know you made an error. That's why we just try and limit it. Where do error and uncertainty come from? As we talked about a lot today, the sampling process. The lab introduces a measurement error. We can add sampling error and measurement error to get sort of a total project error because variances are additive, okay, if the sources are independent. Sampling is independent of the lab. Yes?
So for field sampling plans, what do you recommend in terms of like number of duplicate samples or equipment rinse points, things like that?
You know, I don't do a lot of work in that area. I mean, usually there's sort of a prescribed, say 10% duplicates or blanks, something like that. To me, that's probably good enough. I would rather focus on designing the sample itself, because if EPA is correct, and I believe they are, that 95% of the error and uncertainty comes from the sampling and not the lab. If you have one or two less blanks or duplicates or whatever in the lab, you're probably not losing a lot, something, no doubt. But to me, it's more important to put your time and energy into really focusing on that field sample and then the subsequent subsampling to that. I don't know if that really answers your question. And that I say that because I'm not the chemist. I mean, I'm a statistician, but there's nothing magic about taking 10%. It's a number people feel comfortable with. There's another fellow that does DQOs, and his famous line is, how many samples? 5. Okay, or 30. It's either 5 or 30. Okay, well, where does that come from? Well, 30 we can figure out. 5 is like, people like that number. People just like that number, okay? So, sometimes human nature comes into play. And so people say, well, I don't want to take, they're costly. I don't want to take more. How about 5? We can calculate a variance with, 3. Let's go on beyond what the formula says we can do. Let's do a whole 5. There's no statistical basis really for that, okay? But we do know that if you don't design a sample right, what you could be doing in the lab with all the QA procedures may not be as meaningful as you'd hoped it to be. Does that make sense? Okay. So, and I guess I would also recommend you contact a chemist to get a better answer to that. I personally think 10% blanks is good, duplicate stuff like that. Because, you know, a lot of people go out in the field and they get a duplicate sample. Either they take the material and they split it, or they take them side by side. Well, man, if you take them side by side, to me, you're rolling the dice. Okay, you could get a totally different result, and it's not the lab's problem. You could have just gotten the nugget, so to speak. Okay, even in the sample you split, you know, if you didn't crush it and, you know, reduce the particle size, you could still get a nugget, 1/2 of the sample. So when I see duplicates that don't come back to be the same, you know, the first thing I do is not to point to the lab. I question the sampling and the material. Okay, how was that processed? You know, how big a volume did you take? How was it processed before they analyzed it at the lab? Because there's a high probability that that could be the problem, not the lab tech or the machine or the method or whatever. So. Okay, let's see. There are systematic versus random errors. These tend to come in a lot of times at the lab, but they can be sampling errors if you're biasing, if you're never getting to the bottom of the pile or never getting to the center of the pile. We have a problem over here getting to the center of the pile. That is a bias. Okay, we don't know what it is, but we know it's a bias. All right, we're going to really breeze through this because this is boring. Null hypothesis, this is the snoozer. This is the assumed state of the pile. Is it above or is it below the action level? You know, is it hazardous waste? Is it, you know, toxic for the kindergarten kids you're going to give this compost soil to, or not? Okay, and so you postulate. It's called H naught. Okay, it's equal to 500. Okay, and it's kind of like a court of law. We take that hypothesis and we either reject it, okay, or we don't reject it. Okay, and like in a court, you're either guilty. We never say a person's innocent, or at least the lawyers don't. They say they're not guilty. It doesn't mean they're, you know, they aren't sketchy, but according to the definition of the law, they are not guilty and the jury verdict. Okay, so we do kind of the same thing. We say we either reject it or we do not reject it, even though we may have our qualms about how accurate those data or that decision is. Okay, so our pile can either be guilty or not guilty in a sense. The alternative hypothesis is that it's above. Okay, now usually in environmental situations we reverse these and say we assume it's above, because then you have the burden of proof is on you, the regulated party, to demonstrate that it's really below. Okay, but you can set it up either way. Okay, if regulator says that's fine, that's fine. It's just as part of the confusing part, because the decision errors, type 1 and type 2, then flip-flop. And so even I always, you know, take a pause and say, all right, what's the hypothesis? How's this structured? What does the false rejection, false acceptance mean? And it gets complicated. So a type 1 error, by definition, is that we reject the null hypothesis when it's actually true. Okay? So, for instance, in a court, the null hypothesis is that you are innocent. Okay? If we say you are guilty and you're innocent, that's a type 1 error. Okay? And, you know, different court cases have different standards. Some, you know, beyond a reasonable doubt. Some are preponderance of the evidence. Okay? Those are like having maybe 80% confidence versus 99% confidence. So we kind of do that in our system. This is called an alpha error. I try not to use Greek symbols. Type 2 is when we accept the null when it's false. So we say someone is innocent. We declare them innocent after the trial when in fact he knows that he was guilty. Okay? and we won't mention any names, but maybe we can think of a few people who probably got off, okay? But we also want to make very sure that we don't send people to prison who are really innocent. Of course, DNA testing is now releasing people. So it's a big responsibility there. This, in our world, is called a beta error, or a type 2 error, where we accept the null even though it's false. Where it impacts regulated parties, generally we set up the null to say the pile is dirty. And if they can't prove it clean, it goes to hazardous waste landfill. Well, sometimes, certain percentage, it really was, but the samples didn't show that. Okay, so they end up paying a premium that they didn't have to, but that's what happens. You know, that's why we try and design sampling programs to the best of our ability. We can set up a little matrix here. If the true situation, let's see, okay. Yeah, if the null hypothesis is true and we accept it, well, then we have a high confidence that we made the right decision, okay? And if the null hypothesis is true and we reject it, that's an error, okay? That we want to make a very small percentage of the time. Alpha is that percentage, 1%, 5%, 10, 20, whatever alpha you want. If there's a big consequence, you make it a small alpha. That's not such a big deal. You can make a little bit larger alpha. The other side of that, if the null hypothesis is false, but we accept it and assume that true state of nature really does exist, then we have a beta or type 2 error. And if we accept it, if we reject it and it actually is false, that's a good thing. That's the power of the test, 1 minus beta. Beta is usually set to be larger than alpha because we in our society have decided it's better for a corporation to pay a few extra dollars to dispose of waste that was 95 ppm when the action level was 100 than it is to not dispose of waste that was 150 and we said it was okay. I'm not sure that's right or wrong, but that's what we do. Components, we state the null and the alternative. These are mutually exclusive, okay? There's only two choices, kind of yes or no. We select the significance level, which translates then into a confidence level. We determine the test statistic, which is probably the mean in a lot of these cases. We determine the critical region. We'll talk about that in VSP, where it's kind of a fuzzy zone that we want to manage. And then we compute the value of the test statistic, maybe the mean. We make a statistical decision and report the results. Okay. One of the things you should be aware of are power curves. These are used a lot in groundwater, not so much in soils and piles, but they display the resolving power of a test. And one of the things we know is that the more samples you have, the better your decisions are. It just makes sense. If you have more data, you're better informed, kind of like Abraham Lincoln. Even if they're not quite as perfect on the QC, more data are better. Okay, and the sample size plays a big part in that, in distinguishing between either two means or distinguishing whether a single mean is different from an action level, most specifically below that action level or above. And so here we can draw power curves. We have the true mean on the x-axis ranging from 500 down to 300 or up to 700. And you can see that the power, the resolving power, increases as you move away from the mean. Okay, so if the true mean is 500 and we get a sample result of, if the true mean is 300 and we're worried about 500, then we're fine. Okay, we're good. But you can see that as we get around, if our true mean is 500 and the sample mean is at 482, it's calling it a little close if you only have 9 samples. It's even calling it a little close if you have 25 samples. We could go to 100, okay, and we could it would probably be better. Probably you don't want to spend money on 100 samples. But we might be able to use incremental sampling because our test statistic is a mean. So that's a good thing about incremental. We'll talk about that tomorrow. Okay, I'm just going to skip this. It's basically saying the same thing. You know, when the sample values are low, there's very little chance that there's a problem. As they approach, here's the action level. As the mean approaches the action level, you know, you get more and more evidence compiled that you are above, and finally you're on fire. This comes from Kirk Cameron. If we had perfect decision making, we would have a line. Okay, we'd have the action level, we'd have a mean. If the mean is below, it's clean, and if it's above, it's dirty. Okay? We can't put the whole site, we can't put this whole pasta through this analytical device, so we have to do sampling. Okay, but in order to figure out how many samples we need, we kind of have to hedge our bets and define what's called a gray region. So if this action level is, say, 100, we want to say, okay, we'd be willing to dispose of that material if it's between 80 and 100. Okay? Because if we want to say, well, gosh, no, I'm not disposing unless it's 99%, you're going to take a gazillion samples. Okay? That'll cost, it might even cost you more than disposing of it. So this is a game, and in a sense, you're wagering the number of samples versus the ability to distinguish. And this is basically what the VSP program will be doing. So if your true mean is down here and the sample UCL is up here, you're below the action level and you're good. Okay, so for time's sake, I'm going to kind of go through these. Here's a good kind of summary of this whole null hypothesis. This came from the mining industry where we had ore and waste and profit and loss, and we were very concerned about economics. If your sample assay came back and it said it was below the cutoff grade, and it truly was, here we have the estimated value, okay, based on the laboratory result, which was based on a sample, of course, and here you have the true value, and if the estimated value is below the cutoff, and the true value is also, we throw it over the side of the cliff, and that's waste, okay? No problem. Same thing in the environment. If we prove it's below, and it truly is, we have a good situation, no problem. If our mean or our sample says it's above, and it truly is above, then everybody's happy as well, okay? We made the right decision. The problems come in these two areas down here. And what this is what I call a misclassification ellipse. If you were to actually know the true value and the estimated value, which in mining sometimes we do, because we can estimate what's in the stockpile, we then send the stockpile to the mill tells us what the true grade is based on their recovery, and then we say, okay, I plot the values, we plot them, scatter plot, we draw the ellipse, we draw in the economic cutoff grade, and we get 4 regions, 1, 2, 3, and 4. The problem areas are down here and up here. If we estimate that it's above the cutoff or above the action level in environment, but it's truly below, we waste our money, okay? The mine processes that valueless ore, and we send to the wrecker landfill stuff that shouldn't have gone, okay? That costs somebody money. On the other hand, if we estimate that the pile is below and it's truly above, then we may put that back on the site or sell the compost to, kids or whatever, homes, and they may be impacted negatively. These are health and human health and ecological concerns. These are economic concerns. And so as a society, we are erring more on making these mistakes because they just cost money. Not that that is not significant, but we'd rather do that than hurt people. Okay, that's just the way it works. Okay, so if there is one diagram that kind of sums up the null hypothesis and decision errors, this is probably it, okay? We have our action levels, cutoff values, whatever you want to call them. We have the good areas down here with the bad areas right here, okay? This costs in terms of money, this costs in terms of human health, okay? So I'm going to skip these again. We kind of go through these. All right, again, another picture of the gray region. You know, there's even kind of a gray region above in a sense that, you know, if it really came out at 105, you may always wonder if it were really just below, but that's life, okay. The last thing to cover here, and we don't use this a lot in piles, but perhaps it could be used in some situations. Correlation can be a very useful predictor, especially if you're working with rad contaminated soils or materials, because sometimes, well, rad is very expensive to analyze. So if you can use a field analyzer for one isotope and then extrapolate one or two or several other isotopes based on that, you can save yourself money. Okay, so correlation works in different ways. Sometimes there's a positive correlation. As one variable goes up, so does the other. You get a positive slope line. Sometimes as one variable goes up, the other one goes down. Okay, it can be useful in either situation. Sometimes you get pretty much a scatter plot or a shotgun and there's no correlation. You're out of luck. You have to analyze them both, okay? But it's always worth a try. Various situations. This was a mine where I worked over in Kazakhstan. It worked really well for this sort of semi-environmental parameter. We tracked the heating value, or the BTUs, on the y-axis versus the ash content, excuse me, how much dirty material was there. And there was a high correlation. So in other words, the higher the ash, the lower the BTUs, okay? So what they figured out is, hey, why do a full analysis? We'll just figure out how much ash is there. They didn't have much sulfur. It was like the ash drives the whole thing. Turns out over there, another issue was weight on the trains. You didn't want to have too much weight or you got a penalty. So guess what? Ash is heavier than coal, than the carbon. So you kill two birds with one stone. You decrease the number of analyses, and you also solved your rail car filling problem because you knew what the ash content was and therefore had a good prediction of what the weight of that car and then the whole unit train would be. Okay, finally, we organize the data through statistics. As again, I love to present data visually. One thing statistics is able to do is provide an objective and reproducible analysis. Someone else can recreate that. If not, somebody's doing something wrong. Could be you, could be them. It helps us quantify uncertainty in our decisions and target given levels of confidence. These are always negotiated during the DQO process, and they set a target because in the early days, people would say, well, do I have enough samples? And regulators would say, no, you don't have enough samples. Well, how do I know? Well, we don't like any of it. They go out and they went through the field sampling process, sometimes several times. And they were always like, we want more data, we want more data. With DQOs, we say no. We do the DQA, the data quality assessment. We met our error goals. We said it's above. We take it to the landfill, whatever, or not. It helps us make clearer decisions. There still can be, squabbling it sometimes over details, but it's really been effective over the years. And based on our knowledge of sampling and statistics, we can minimize the decision errors by design, up front. And as Tressa was saying, and you were saying, do this up front. Get it on paper so that everybody understands the process, everybody understands the expectations, everyone understands the decisions, the null, the alternative, what's going to happen when the data come in. Not perfect, but it's as good as we've got.